Hello, everyone. Good morning, good afternoon, good evening, based on where you are. Welcome to the first CAD for Assurance tool training session or webinar. So while we are still waiting for people to join, I would like to start the introduction of this web session and the background why we have these webinars. So I'm Jing. I'm a faculty member at the University of Florida. So supported by IEEE CEDA, by IEEE Hardware Security and Trust Technical Committee, HSTTC, and supported by the University of Florida, the NELMS Institute for the Connected World, supported by all these entities. So we create a website called CAD for Assurance. So I think many of you, if you join this webinar, you must have already known this website. So the key idea is to promote the hardware security research. People may ask, so what's the difference between this website and other website? The key difference is that in this website, we are not just trying to introduce you the new techniques, but we would like to see how these new techniques will ever be converted into real-world applications. Some algorithms and some programs would all be posted there so that as researchers, we can test it, we can validate that. And more than that, I know many of you have the experience that you read a good paper, you like the idea, you cannot find the code. And eventually you contact the author, you get some code, it may not even compile. So this is actually the way that blocking the research, blocking the way that we want to disseminate our research outcomes. So that's for that reason, we initialized this webinar. We invited the authors of these tools to introduce these tools by themselves. So that's the reason that this webinar is different from all other webinars you ever attended. The authors will not spend much time, the speaker will not spend much time to introducing the technology, why it's great. Instead, the speakers will spend the majority of the time just to tell you, this is my tool, you must have already heard from their papers. And this is the way that the authors to demonstrate the tool for you. In this way, we would like to encouraging the latest trends we called open source EDA and open source hardware for security. So with that said, I would like to introduce the speakers for today's session. We have two sessions on each webinar. The webinar happened on the second Friday, 11 to 12:30 Eastern time in US. So based on where you are from, you may do some calculation. It's around midnight in China. It's around very late night in India, and in Europe, it's in the afternoon. So, and I also want to remind everyone, all the webinars will be recorded and will be posted both on the IEEE CEDA archive and on the IEEE CEDA YouTube video. So if you miss some of the talk, you would still see them on our YouTube channel. So Sarup, I see you are there. Do you have anything to add before I introduce the speakers?
No, you have done a great job here. We do appreciate the support from IEEE CEDA, IEEE Hardware Security Council, which is a technical committee under IEEE CEDA. And in particular, would like to appreciate significant help from Amanda Osborne from IEEE CEDAS. She has been instrumental in creating the website for this event and sending invites, setting up the Zoom links, everything. So Amanda, thanks a lot for all the help. And yeah, as you mentioned, this particular event is very unique. This is probably the first ever in virtual event where we are giving demos for academic CAD tools, and we are also having an information session on that, so that if anybody would like to adopt it for either research or practice, that would be possible. So this is a unique opportunity. At the same time, the nature of the event is also very unique. So I do appreciate everybody for participating. I do appreciate the researchers who agreed to share their tool to the broader community, because that's a very important thing to spread the significance of hardware security research to the overall community. And that's why I think it's a very important event. Thanks everyone for supporting this. So with that, I will hand over to Yer.
Okay, thanks, Aru. So yeah, I just let's start the webinar. So today we have two webinars. The first webinar is from Travis Meade and Jim Geist introducing their NETA Toolset. This is a netlist, gate level netlist security analysis toolset. And the second is from Dr. Chester Rebeiro. He and his students will introducing three tools: FEDS, Safari, and XFC. Okay, so with that said, I would hand the podium to Dr. Travis and Jim.
Thank you very much here. And thank you, IEEE, for setting up this event and allowing me to be one of the first presenters for CAD for Assurance. As was mentioned before, my name is Dr. Travis Meade. I am a faculty member at the University of Central Florida in the Computer Science Department. And I'm going to be co-presenting with my PhD student, Jim Geist. He will be talking later on in the series, demonstrating his own tool that he's been working on. But I'm going to be focusing on some of the tools that I worked on when I was a PhD student and what I worked on a little bit afterwards. I've been supported by NSF and DARPA, and I would like to thank them as well for helping me get this tool set up to what it currently is. So I'm going to not try to bore you too much with the motivation, but the idea is that there are a lot of integrated circuits in a lot of everyday objects, and these embedded systems are kind of taking over a wider range of appliances, from things that are just some simple at-home devices to things that might be mission critical. And the idea is that there's this huge influx of these integrated circuits, and unfortunately, it seems that the methods that we use to analyze these intellectual properties that's associated with these might not be accelerating quite at the rate at which the production is increasing. So we need to go ahead and work on analyzing these devices more efficiently and more accurately. And so that was my general idea and goal with the NETA toolset. So with the analysis tools that exist out there, there are a lot of tools that will actually take the netlist that's in the hard silicon, and it will turn it into what's known as the gate level netlist, which is kind of involves doing some sort of chemical stripping, and then doing some imaging, and then kind of doing some analysis on these cells to go ahead and figure out what behavior they are having. But there's not a lot that goes from that gate level information to a higher level that might be easier to understand. If you give some designer a gate level netlist, it might be difficult for them without information as to what the golden netlist is supposed to look like, to determine if it's supposed to be, if it's behaving appropriately. And it might be the case that someone is receiving some sort of third-party IP that's delivered as this hardcore gate level design, or potentially something that's a actual silicon device, and they don't know exactly what it's supposed to be doing. And they might not know necessarily even some of the RTL that would use to generate this either. So there's like a potentially this huge knowledge gap between what they want to do and what they're actually getting. And the goal is for us to go ahead and kind of bridge that knowledge gap by doing analysis on these gate level designs. So we can kind of imagine that integrated circuits are developed in kind of like this flow that's represented at the bottom, where you have some intellectual property, you can develop some specification that turns into some RTL, you do some synthesis on it to go ahead and place and route and get some gate design, and then that gate design is sent to some foundry for some fabrication. And the problem is that, like, really, if you're given like those last two aspects, it can be kind of difficult to determine what might be happening. There might be, depending on like where you're, getting involved in this, like if you're only like really like trying to get the IP developed and you have kind of like what you want to get developed, you might like outsource some of these steps to other groups that might be potentially like either inserting some like debug or some test behavior in there that you're not aware of. There might be some specification that's not actually defined that's being put into the RTL or into the gate level netlist that you wouldn't necessarily know unless you tested it very thoroughly and eventually found it, like potentially when you're trying to do some stress testing. So there's like a lot of these different situations that could require some sort of analysis, but unfortunately there's not a lot of stuff that works from the gate level to get to the RTL or get to the specification to determine if things are appropriately matching what they should be matching. If you have the golden design, you can do some analysis, but again, like the idea is that my research made the assumption that we might not have access to these, and so we tried to work without them to go ahead and do this analysis. So the first step will be to go ahead and take this gate level netlist and to turn it into a signal graph. And then from that signal graph, we should be able to do some analysis to go ahead and figure out like what the logic is inside the design. We extracted that logic as we typically represent it as an FSM. And then what we're able to do is we're able to take that FSM and extract the actual RTL code behind it. This all involves like a series of different frameworks to actually store the data, such as netlist, netlist library, and modifiable netlists. And in addition to having all these different things, we require like some advanced algorithms to do this sort of analysis, having to do like parsing on these files to kind of understand what they're actually they're supposed to be structured wise, and also to do the analysis itself on these designs requires some sometimes advanced algorithms that might not be easy for someone that's just trying to do some integrated circuit development to actually code up. And that's so we wanted to make all those processes automated and easy for people to use. So we start by, as I mentioned before, trying to analyze the netlist to go ahead and look at the signal graph. So assuming that we parse everything correctly and we have now this graph structure, what we're going to be using is some tool to go ahead and look at these designs to go ahead and say what might be a signal of interest, what might be potentially logic. And now logic can be either benign or malicious. It could be something like the actual finite state machine or the logic that will actually control the data flow of the design, which can be a good thing if you're trying to like go ahead and move like some addresses around or some data to different locations. It might be something where you're keeping track of like what state the design in. Are you idle? Or are you trying to read? Are you trying to send an acknowledgement? Or it could be something where maybe saying whether we're going to be leaking some information or not. So potentially hardware Trojans. And we've tried to make this a very general purpose tool that will work on any sort of logic extraction. So the tools we have are available are things called Relic, RePCA, Relic Fund, and Rebus. Relic's goal is to go ahead and look for unique fan-in structure at the gate level to go ahead and find potential logic. The idea behind this is that things that are data typically undergo similar modifications or operations. And because of that, their fan-in structure is going to be repeated for every bit in their word. So the idea is that something that's logic that doesn't actually have like a word associated with, but maybe just like a state machine that's composed of like just a couple of FSMs is going to have a very unique fan-in structure. And so we go ahead and look for the unique fan-in structure using Relic. And the original design of Relic was to go ahead and do this pairwise sort of comparison, which is not very efficient. We eventually published a tool that did some principal component analysis to make it so we don't have to look at every pair of registers to look for a unique structure. Instead, we were able to look at only a few of them. It ran a little bit faster and sometimes had better accuracy depending on the design. Another tool that we've developed and published recently with something called relic fun, which rather than looking at the actual gate level gate structure, we look for unique signal function behavior and then use those to do analysis. And we've also done kind of a reverse sort of process where instead of looking for the logic, we actually look to see if we could find the data bus by using a method called forward propagation that's been mentioned in other works in combination with the relics structure analysis. So it allowed us to find some words and do some partitioning that was not strictly at the logic level. So how you'd actually use this tool, we have like a lot of arguments and command line functions that you can use. So here would be an example of what you would do to run it. You would do logic identification, going into binary files and using relic. You'd pass in the name of the library and the name of the netlist we're doing. For this demonstration, we're using like a very simple UART communication protocol, which is something that just like transmits and receives data. And if you run relic, what you're going to get is a lot of output. And it's like it'll say that it's reading in the netlist. It'll say like kind of the size of the design, and it'll say for like every register, basically the ID that it was given based off of our program, and it'll also say the name of the signal. In addition, it'll say what z-score it got, representing kind of how far away it is from like the average gate structure. And so in this case, what we're really looking for is we're looking for things that are kind of abnormal. So what we would be looking for is something that has a very high z-score, something that's very far away from the structure of the other designs. So what we typically do is we have this data sorted actually from the lowest z-score to the highest z-score. So unfortunately, when you want to find the things that are potentially data, you're going to have to go to the bottom of this list. And so at the bottom of this list, we have like these wires here. The z-score, you can notice, kind of has a significant jump at the bottom. We go from like being in the 1s to go to 3 to 5 to 20s to 30 to 60. And a z-score of 60 is very significant. So that's like very unreasonable. But we would go ahead and use this element to go ahead and probably to see what like type of logic it is. So N25 is probably an interesting wire that we'll try to analyze, but we wouldn't be doing so with this logic identification tool. We'd have to use something else. So how we actually examine this logic once we have the signal in question is we would use one of our logic extraction tools. We have a couple different ones that are of interest, ReFSM, the original one, and ReFSM2, which was published later. ReFSM1 is one of the first publications I've ever done. It was like, I think it got a best paper award in ASP.DEC. And now I think I know it got a best paper award in ASP.DEC. So its goal was to take some set of signals and to go ahead and extract the FSM behind them. And we included in that the ability, if you potentially gave it extra information, so there was some finite state machine flip-flops that were combined in addition to the FSM you were interested in, we had a way to go ahead and separate the two FSMs from each other so that way you could go ahead and analyze them independently. ReFSM2 came about later, where we allowed ourselves to look for signals that kind of converged into like a fan-ins that converged into a single signal, which allowed us to go ahead and improve the speed at which ReFSM was able to do the extraction because it didn't have to expand certain wires to see like their input behavior. We also developed some tools that generated finite state transducers, which basically means they have FSMs with outputs. And that's useful for eventually determining the RTL code of the original design that's in ReRTL. And then we also have repath, which can basically tell you what input pattern is used to generate a certain state from your FSM, which is useful for like looking to trigger potentially rare occurring behavior, which would be nice if you're trying to determine if there's potentially something malicious in your design. You could run that, see what ends up happening, like see how you can trigger it, and then like use that input in your own design to go ahead and notice the behavior of your device, and if it behaves in a weird way, you would know, okay, this is potentially dangerous. We have some like additional versions of ReFSM that we're working on in the meantime, and we'll be releasing those as we get them finished. But like ReFSM was kind of meant to be kind of like an initial starting point, and it kind of created this whole NETA Toolset in the first place. So what we're going to do in this example is we're actually going to use ReFSM to analyze that N25 wire from the original design. So what I have here is an example of like what you would see in the words file. So in the words file, we would go ahead and say that we have one signal what we're looking at, and that's the N25 signal. And what we would do is we would pass into ReFSM not only the net list and the library we're using, but also that Word file that we're using, which is just the N125. If we would go ahead and run this, and we would get some very simple FSM. It says that it's able to go from state 0 to state 1, and from state 1, it's able to go to state 0 and 1 as well. So it's not a very interesting FSM at all. It does actually look for the reset, and you can see that it found that system reset L was probably the reset signal, which makes sense since it's named reset itself. But this doesn't really give us a lot of information. So if we want to actually do further analysis on this, we want to see actually kind of what conditions are causing this sort of behavior. What makes the signal go from one state to another? So we can actually run this using this flag --const, which basically says print out the conditions. And when we run that, we get this much larger FSM with like the input information now provided. And you'll notice that there's like these certain transitions that require like this huge line of potential behavior. All of these are required to be triggered at once. So you can imagine like we have to have N13 be 1 and XMIT H be 0 and N67 be 1 and so on and so forth. Now, the things that are of interest to us, though, are typically the ones that have high control over our value. So what I actually am interested in are these ones that are able to cause a flip of the value from 0 to 1 or 0 to 0 by just having a small amount of control. So these two signals here are interesting to me because they're able to affect the behavior of design. And the N103 is actually very important based off of this behavior because it has a pretty big control over how this behaves at when the value is just 1. So I'm going to go ahead and include both of these into a new Word file. I'll re-extract the new FSM and see what type of behavior I end up getting out. So I now have like this new Word file I created. There's 3 signals we're looking at. It's N125, N113, and N103. And I'm going to go ahead and rerun with this updated Word file. And I get something that looks more like a real FSM. And if you drew this out and compared it with the XMIT FSM in the UART RTL code, you would realize that they actually are the same pattern. The only thing that might change a little bit is some of these signals might be complements to the other ones. So like the ones might be flipped or something like that for one of the bits, depending on like what's going on here. But this is great. So that means we're able to go ahead and extract the correct FSM, and we're able to do so using only a little bit of effort. But we have some other tools as well that's not just for logic extraction. So we have some tools such as Targens, RedPen, and ReBFS that can like help with doing analysis that my students have found useful when trying to analyze designs. So Targens is a algorithm. Targen is a very famous computer scientist. He came up with a lot of graph theory and graph problems and then graph algorithms. And one of his famous ones is his strongly connected component algorithm, which is useful for finding nodes that are able to interact with each other. And so we use that to go ahead and find nodes or registers that are able to interact with each other, because there's a good potential that those end up being logic in unobfuscated designs. And in fact, the strongly connected component algorithm was an early algorithm that was used in netlist analysis to determine where potential finite state machines would be potentially located. The RedPen is something that we use to actually extract the register relationships. That way we're able to actually use the Targen algorithm. But Targens is also able to be used on the actual FSM you get as output to go ahead and see where there might be sinks or source FSM state groups, because those can be useful for determining where black hole states might reside if you're looking at something that's sequentially locked, or if there's potentially like an unlocked state group, you could find that using this algorithm as well. ReBFS has been used for analyzing and looking for potentially logic locking wires. We've used that in the past before. And the idea is that it basically extracts the fan-in of these different signals that are within the design. And we have done scripting with it to go ahead and get some interesting results in the past, but it's something that's like available to be used. And it's again been useful to my students at one point or another. So if we ran RedPen on the UART design, we would end up getting like this huge transition list, and it would be kind of hard. Like, you can see like this signal here will interact with this signal here, and you can see like this long list of signals, and it might be difficult to go through this. There's like several hundred lines here, and it's kind of challenging to go through and say like what is important and what's not important. So what we would do typically is we would take this entire thing and we'd write it to a file by using an out flag. And so now what we have is a transition file that we can go ahead and do analysis on using targens. And so if we run targens on that transition file, we can see kind of what the groups are. So this wire is alone, this wire is isolated, this wire is isolated. Like a lot of these registers don't interact with other ones. But then there's like this group of wires that's really interesting. And you'll notice that there's like an N102, an N101, N100, N99, so on and so forth. There's like a lot of different signals inside here that would be of interest. And some of them include like N113 and N103, which are ones that we had seen in the past. One of these wires is actually the complement of the 25. I think it might be it's either the 102 or the 12. It's been a while since I've looked at this. But this is like a really strong indication that this is like potentially a large FSM here, and we could do analysis on it and then potentially use tools to split this up. But like at the bottom of the output of the target files, it says like, what are the source SECs and what are the sync SECs? And in terms of looking at logic, the FSMs that are typically the logic tend to be the source SECs of your register transition. So the N group, which has 12 wires in it, is a good potential of being logic, and we would want to do some analysis on those in the future. And that's how you could use like the targens method to do netlist analysis as well. But so now what we're going to do is talk a little bit about Jim's tool, which is Netviz, and I'll let him take over at this point. Jim?
Yes, can you unshare your screen?
Yep.
Oh, thank you. So I am going to hopefully, okay. Can everyone see my screen now? So hi, I'm Jim Geist. I'm a PhD student in the NETA group working with Dr. Meade. I'd also like to thank IEEE for helping us put this on, and NFS and DARPA for funding our research. As Travis said, I've been working on a tool called Netviz. And the motivation behind this, as you can see, we have a bunch of great tools. And the way all of them work is they take a text file as input, and then they transform it via some kind of complicated, cool graph analysis algorithm. And then they output to another text file. And then you take that output from that text file, you edit it somehow. As Travis was showing, you take the output of Relic, you edit it down to the registers you're interested in, and then you create a words file for ReFSM. And you keep rinse and repeating this through your workflow as you gain more and more information about the netlist. So that works, but there's a couple of downsides. One of which is there's a lot of text file editing, and that's kind of tedious and error prone. And the other problem is that, as Travis intimated in a couple of times, it can be hard to see patterns in output of any size. Like with the register dependency graph on a netlist of any size, that can be thousands and thousands of lines. And our brains just aren't built to work that way. Our brains are built to look at for patterns more graphically than that. So what we would like is a meta tool that wraps all of these other tools. And we want to make moving data between all of these tools easy. And we also want to be able to see these results in a visual language we're used to. And in this domain, that's usually graphs. These things split naturally into graphs where you have nodes and edges, whether the nodes are gates and the edges are the connections between them, or the nodes are states in the FSM and the edges are the transitions. That data structure comes up a lot. So what I decided to do was write a visual tool. Now, I will say this is a remote, this is a work in progress tool. This is not shipped yet into the NETA Toolset, but we hope to eventually. That wraps several of these existing NETA tools with more to come, that tries to display data in a more natural form and also give graphical input to these tools. So I am going to bring up my desktop and then bring up Netviz. So you can see here, this is the Netviz tool. And the starting screen here looks pretty much like any other CAD tool you've ever worked with that shows a gate level schematic. And you can do all the standard things. You can zoom in and out, scroll around in this and investigate. And we have a signal list over here. If I wanted to say just look at XMIT stuff, I could filter down to just the XMIT signals. You can select gates in here. You can even run BFS, and it will show you to however many levels you want. Like, okay, this is colored by shading as to how far out from the gate you are. The really bright wires are direct descendants of this gate, and then they kind of fade off as they get farther and farther away. But really what we're trying to do here is run the algorithms that Travis was talking about on this net list. So I'm going to show, first of all, one thing. There's this box down here, constants. Travis showed that ReFSM and Relic will go out and find the reset signal for you, but sometimes, especially on a big net list, that can be slow. So we also have the ability to tell the tools what the reset signal is. And the way you do that in the tools is you create yet another text file and put that information in there. Well, here we're just going to click on what we know is the reset signal, and we're going to mark this as a reset low. And now you can see down here we have sys reset L is a reset low, and now that's just available to all of the tools that we're talking about. So obviously in a graphical tool you can make selections. Selections are kind of how Netviz communicates between any of the tools. So when a tool has an output, typically the output is in terms of some set of gates. So a selection is just a set of gates, and we can actually save that and come back and work with it later, which is very useful. A lot of times when you're iterating, you're going to change the selection and run a tool again, but you might want to go back to what you had before and rerun a previous analysis. All of this stuff gets saved in a project that's associated with the net list. And this net list, by the way, for the sake of consistency, is the exact same one that Travis was working with. So we're going to go ahead and do the same thing he did, and we're going to run Relic on this net list. And as you can see, this is the exact same results that he got, but in here they're in this tabular form graphically. And again, he started with just N25. I'm just going to pick the top so many. Pretty much we think everything with a high Z-score here is probably interesting, and we want to see how they're related. So I'm going to click next. So now we're starting to get into something more interesting. This visualization is actually showing you, Travis talked about red pen. This is a visual representation of what red pen would give you just on those registers that we selected from the output of Relic. So you can see here we have two different clusters of registers, and down here we have 4 registers that seem to be strongly connected to each other. So what these arcs mean is N103 affects 113, N113 affects 112, probably through a bunch of intermediate combinational logic. And this pattern where all the registers can affect each other is similar to the SCC concept. This is most probably an FSM. And so we want to run ReFSM and look and see if this looks like a reasonable state diagram. So here I can just select these nodes, and that's going to provide the input to the next tool without having to edit anything. So the next tool, remember, it's going to get this reset signal, and it's also going to get these 4 gates. So now I'm going to go ahead and I'm going to run ReFSM. And now we have something interesting. We have this FSM has 2 SCCs. This is interesting. Is basically each of these states in this diagram is an SCC of the states that are inside the final FSM state transitions. So there's 1 state by itself, and then 5 states which can all reach each other. And we want to be able to visualize that. A lot of times, sometimes this is just because you have an entry state that then leads into the working states of the FSM. If this was more balanced, if we had a bunch of states in this first FSM or first piece of the FSM, and then we had a bunch of states here, then something weird might be going on, because a lot of times what you'll find in malicious code is that you'll have an FSM that does some malicious stuff and then dumps you back into the original FSM and makes the design look like what it's supposed to be doing. So we can click on any of the stuff to go in and actually see the states. I'm going to click on the edge because that's going to show me this state transition diagram. And you can see here that we do have this entry state, and then we have these 5 states which we can move between, which happen to be the working states of this. And this is the XMIT side. This design is a UART, so it actually has a receiver FSM and a transmitter FSM, and I'm working with the transmitter FSM here. But you can see, we can very clearly see how these transitions lay out. We can see this is color coded, so you can see this was the one that was by itself in the previous slide or previous screen. And this is much easier to work with than just a text file with a list of transitions in it. And you can also go back. I could go back and then just investigate these 5, or I could go all the way back and choose different gates. So as I said, this is a work in progress that we eventually hope to release, but we hope people will find it useful. We're also we have plans to make this a plugin architecture. Right now, you can see it has quite a few of the tools that Travis talked about already integrated in here, but we would like to make a plugin interface so people can even plug in tools from other research groups and be able to visualize their results and even take input from the, let's say, the output of our tools and make them all work together. It's meant to be just a generic hardware security workbench. So that's Netviz, and yeah, I hope you find it interesting. And I'm gonna stop sharing this, and then we'll go to Q&A.
Thanks. So yes, please feel free. Thanks for the speaker. Please feel free to type in your questions in the Q&A window. I think we do have one new question: how to deal with the feedback and the loop in the netlist? Travis or Jim, can you see the question?
Yeah. Do you want me to answer it live, or do you want me to type it in?
No, just answer live. So no
okay, yeah.
Q&A session.
So in order to deal with the feedback loop, like you can have, like, you know, when you have these things that are temporal, you'll typically have like some sequential behavior where like you can have like some wire indirectly affect itself. That happens especially when you're in like a state machine that needs to be able to transition to different things. So what we end up doing is we just create like a series of wires that will like a series of edges in a graph that will connect back into itself. And what we do to go ahead and determine like if it's on a different clock cycle or not is we actually in our graph representation, we don't split the node into like a past and present. We actually use the same node, but we'll say that there's potentially 2 states associated with this by saying that this is a some sort of temporal logic behavior. So like it has like we assign basically some extra value to it that says that it is a flip-flop or like a latch or something to that extent that has like the ability to be a value in one state and then like have some next to value that's going to come in to update the value in a later state. But you can just you can like create the cycle in a graph structure. And when we're doing something like Relic, you might go infinitely deep if you're trying to look at the fan-in like recursively. So Relic actually has a cutoff that prevents it from going too far back to make it so that way at some point it'll stop when we're doing the fan-in comparison. So we in Relic, how we handle it is we just use a cutoff, and ReFSM we just use like a value to say that this is going to be 2 different states. If you have something that is that has a loop in it and it doesn't have like a flip-flop on it, like if you have like a ring oscillator, we don't really like emulate that behavior because the ring oscillator is going to act independently of your clock cycle. It's just going to keep updating. So like that's like not a good thing to have potentially. So we kind of like will ignore those type of components when we're doing the analysis. So the advantage of having the FST is that the FST can actually output the output of the FSM. And FSM will have like some next state it goes to, and it will have some output signals it'll send to the rest of the signal. And like if you have a control FSM, you can go ahead and see like where those outputs are going to say that those are the control signals, and you can use those to kind of like determine like what the data should move in what state. And so that's the benefit of having the FST. Should I do another one?
Yes, the second one, please.
Okay. Can the tools handle asynchronous logic? Not right now. We have no plans currently to do it. Like we're not like working on that right now. That is something that's like on our list of things that we want to do. But we have like other things that we're trying to work on before we work on the asynchronous logic. Sorry about that. Do you have a select window history of the FSM? That would be something for Jim to answer. Jim, can you do that?
Sure. I'm not quite sure what you're asking. How do you select the window history of the FSM to track? So, I mean, you select the FSM or what FSM you're interested in just by clicking on the nodes in the FSM. I mean, all I was doing when I selected the FSM to go work with it was use the mouse, and I went in and clicked on the component nodes. And from Relic to get to the list of registers to look at, right now it assumes that the top Z-scores are the ones you want to look at. Like Travis clicked one or used one in his demo, and I see in the chat he said that he normally just looks at the top 20. So in that screen, all you do is pick how many top N ones you want to look at, and just click next, and it goes and analyzes those registers.
So limitations for the tool. I mean, there's obviously like certain ones you can make. Like if you make a net list that's too big, like we're gonna run out of memory. But like it takes a lot of effort to do that. Like we've run this with like hundreds of thousands of gates, and not only have we run with hundreds of thousands of gates, but we run it like in parallel where we had like multiple of the designs stored at once with hundreds of thousands. So in theory, we could work with like millions of gates. We have had we do have some like stuff that's kind of like in like kind of just a limitation of like how certain like data types work. Right now we're using ints to store states. So technically if you make like a number of states that's larger than integer max value, that's going to have some issues, which really that's going to basically depend on how you're selecting your FSM flip-flops. So if you select like a subset of your FSM, you could in theory make it like smaller than integer max value. But it also means that if you use more than 32 signals in an FSM, ReFSM doesn't like that. So we do have plans to expand that to make it so that way it works with an unbounded number of signals, which could work with, you have like a one-hot design, like where one bit is on for every state you're in. Although that's like a really big waste of memory, and hopefully you're not doing that in practice.
There's one other limitation we might want to mention, Travis, which is that all of our work has been centered around ASICs.
Yeah, that is true. Not
FPGA. So currently we don't support LUTs in our simulation. We only support the basic logic gates.
Okay, thanks. So I think we are running out of time. I would like to thank Jim and Travis for the great presentation. I want to, before I introduce the second speaker, I want to mention two things. First, this webinar and the whole CAD for Assurance website has been strongly supported from IEEE CEDA and the IEEE HSTTC. The Vice President of IEEE CEDA, Dr. Zhongyi Hou, is here. And the chair of the HTTC, Gang Ku, was here also. So I would appreciate their support. In fact, today is the Chinese Lunar New Year. So I really appreciate they attended the talk. And the second thing I want to mention is all these tools which are introduced may not be entirely, but at least part of that has been released on the CAD for Assurance website. And that is the criteria when we selecting speakers. We want to make sure for those speakers, their tool, at least a big portion of the tool has already been on the website. So you can, after you're taking the attending the talk, you can just download the tool and play with this tool. So this is the one key criteria. And if you have more questions, definitely contact the authors directly. And this is our goal, to promote the whole hardware security research. And with this said, we have the second webinar second tool training session from Dr. Chester and his students. Chester.
Hi, Wire. I'll just share my screen.
Yes, please go.
So thanks, Wire, and also thanks, CEDA, for this great effort to actually showcase hardware security tools. I'd be talking about some of the work we've been doing on automating fault attacks. So this is joint work with students, PhD students and master students, and also collaborations with Professor Swarup Punia and Aritra Hasra. And also a big thanks to Cisco for actually sponsoring a large portion of this research. So we've started working on this particular set of tools roughly around 2016 or so, and so far we've got around like 4 tools which are up, out of which 3 are present in the website. They're open source and you could download and play with them. So let's just get started. So what are fault attacks? So a lot of these tools as of now are specifically for ciphers, specifically for block ciphers, but we do plan to extend them for general purpose, general hardware and SOCs. So when we talk about fault attacks for ciphers, what happens is that we have an encryption which takes a plain text and a secret key to give you a ciphertext. But in a typical fault attack, you would have an attacker which disturbs encryption by injecting a fault. The fault could be temporary in nature. It could just flip a bit momentarily, or it could actually create a stuck-at fault somewhere during the execution. And if everything goes right, this fault propagates through the encryption, through the hardware, and eventually results in a faulty ciphertext, or the ciphertext which has errors due to the fault. The attacker would then compare this faulty ciphertext with the actual ciphertext, perform some analysis which could involve applying some cryptographic properties of the cipher to extract secret key, extract bits of the secret key. So the critical aspect is the fault injection, and if the fault injection is right with respect to multiple aspects, like with respect to the exact location where the cipher is working, cipher is performing operations on the chip, the exact time and the exact intensity, then the faulty ciphertext would be actually exploited to reveal bits of the secret key. So the typical way the faults are injected are through laser, or even much more cheaper mechanisms like injecting glitches in the clock or the power lines of the chip. And as mentioned before, these need to be exactly precise to exploit the fault. So a lot of research has started on fault attacks. It started with the AES block cipher. A lot of papers have been published, especially in between 2000 to 2010 or so, which evaluated how faults could influence influence a cryptanalytic or a fault attack, right? So what was actually found out that a bulk of an AES chip is immune or cannot be exploited when a fault is injected, but a very, very small percentage of locations within this AES chip which can be exploited by a fault attack. So a fault in any of these locations in the AES chip could actually result in a faulty ciphertext, which then could be exploited. For instance, if a fault is injected in the 9th round, then each fault could reveal 32 bits of the secret key of AES. While on the other hand, if the fault is injected in the 8th round, then a single fault is sufficient to actually reveal the entire AES key, that is the entire 128 bits of the secret key. Now, this is with respect to an attack known as differential fault analysis. And with respect to this attack, if a fault is injected elsewhere in the chip, it cannot be exploited. So for instance, if you have the faults injected in any of the other rounds, maybe from the second to the seventh round, the fault cannot be exploited. So a lot of the research in fault attacks on AES was done manually. So it started in 2003, and it took several years to actually evaluate the complete AES, map out all the operations which are actually exploitable, and also to identify how exploitable they are. So here we denote how exploitable by the number of key bits that a particular fault can actually reveal. So eventually in 2011, there was this work by Sakiyama, which showed that um, that the entire fault space of AES was covered, and no other faults could be possibly found in the future that could enhance the attack with respect to differential fault attacks. So the aspect is that this entire research, which spanned over 8 years, was only for one cipher. And with new ciphers coming out quite regularly, with competitions from NIST with respect to actually developing lightweight ciphers, it's still a very manual process to take each cipher, evaluate it, and then maybe another sequence of years before the fault space is actually mapped. So this is what we actually started off with, and our objective was to actually develop a tool which could automatically evaluate a cipher and its implementations for its fault attack vulnerability. So we started off with this tool called XFC, which is a framework to evaluate block ciphers for differential fault attacks. So at a very high level, what XFC does is that it takes a block cipher specification. So this is a specification. It's a language which we have developed, known as this block cipher specification language, which can be used to represent a cipher at a very high level. And importantly, it could also capture specific properties of the cipher, like its differential or algebraic or impossible differential properties. We also, XFC also takes as input a fault model, which would tell you what type of fault that you want to evaluate. For example, a temporary fault, a stuck-at fault, and so on. As well as that it can, the model also tells what position of the fault that you want to evaluate. So there is a sequence of operations that XFC does, and then eventually gives out a list of keys which are possibly exploitable with respect to this particular fault model. So for instance, if we actually give as input the AES cipher, the output of XFC would be the list of keys that can be derived when a particular fault is injected. The second output is also the complexity of the attack, which tells you the offline complexity of a specific offline complexity to essentially obtain a secret key. So if you take AES, for instance, AES has 40 functions spread across 10 rounds. And out of these functions, there are very certain, a handful of functions which are actually exploitable. So this is around the 7th and 8th round and 8th and 9th round. So if a fault is injected within the 7th and 8th round, it would give us 128 bits of the secret key and have an offline complexity of 2 power 8, which means that the 128 bits of the secret key is now reduced to a space of 2 power 8, that is 256. So all of this is actually done automatically. So the way it actually goes, this gives a bit more detail about what XFC actually does, is that the block cipher specification is in this language that we've created, known as the block cipher specification language. It looks very much similar to HTML, where you specify each function present in the cipher, but you also specify other aspects such as whether the function is linear or nonlinear. It also could specify aspects such as how nonlinear a function is, or what are the differential properties of that particular function, and so on. The second input, which is a fault model, would be one specific line which you in this block cipher specification, which you would want to evaluate. So given this, you would end up getting the required output. So at a very high level, what XFC does is that it uses a kind of a coloring scheme to propagate faults across from the point of origin, that is over here, for instance, and up to the ciphertext. Now, each color means a particular relationship. Each color essentially has a particular meaning, and it essentially all lines with the same color are highly correlated. So the essence of this entire idea is to find within the specification equations of this form, where the left-hand side has these this very specific difference equations, while the right-hand side has linear functions in delta. So delta essentially is used by the attacker, which is a difference that is introduced by the fault. So the more number of such equations that are found would imply a stronger attack. So I'll not go into details of how this works, but it's always available in the paper. Now, we started off evaluating AES, but then extended it to several other ciphers, both Fiestel as well as lightweight ciphers, even more recent ones like Present and Simon and Spec. And these were the results that were obtained. So the follow-up work that we actually had also showed that the algorithms used to identify these fault vulnerable operations of a cipher are both sound and complete, which means that if XFC mentions produces an output which says that a particular operation is vulnerable to a differential fault attack, it means that it is indeed vulnerable, and the set of such operation, there's nothing else which there's no other operation which no other of the operations which are actually not vulnerable. Okay, so given this as our starting point, we actually built several tools which could be used both to evaluate new cipher operations, as well as used it in to evaluate Verilog as well as C code. So of course, the base tool is XFC, where if you're given a new cipher algorithm written in the BCSL language, XFC would be able to actually derive all the exploitable regions of that particular cipher. Another tool that we actually had was called Safari. So what Safari did was, again, used XFC as the base. It would take the BCSL input of a cipher, and then it could actually synthesize either a software implementation or a hardware implementation in Verilog that was immune to fault attacks. So the essential idea is that we would take XFC, we would take the block cipher specification as input, use XFC to identify the exploitable regions in that specification, and then based on the user requirements and the security level required by the application, this is then used to insert countermeasures into this block cipher specification. So finally, this is used to synthesize either software or hardware code. What we do achieve from this is hardware or software which is much more optimized, but yet can provide fault attack security, just like any other countermeasure which is more naively actually put. So here, for instance, it actually shows the overheads of a hardware implementation of AES with countermeasures inserted by Safari. So what we do see is that first, Safari could actually choose between different types of countermeasures that would be introduced into the hardware, depending on what type of security level is actually required. It could go from something very simple like 1-bit parity, or the other extreme to get higher level of security. You could actually, it would automatically choose to have a completely temporal or spatial redundancy. Now, what we do achieve is that in spite of, since these countermeasures are inserted very specifically at locations which are vulnerable, the fault coverage, which is shown by this line over here, doesn't actually diminish much compared to a naive countermeasure approach. So similar kind of results could be also used with the AES software to get very precisely inserted countermeasures. A third tool that we had, in fact, the third and fourth tool that we had used XFC again to map the vulnerable regions onto an implementation. So unlike Safari, where which has essentially synthesized either Verilog or C implementation, either hardware or C implementations, here on the other hand, we took an implementation as input, used XFC on the block cipher specification to identify what operations or what gates in the implementation are vulnerable. So at a high level, this is what would happen. So the algorithm specification is the input to XFC. We would use XFC to identify which operations within this algorithm are vulnerable to fault attacks, and then have a mapping tool. The mapping would essentially map or identify where in this implementation, which could be either C or Verilog, are these operations actually inserted. So this way, for example, in a hardware implementation, we would know exactly the exact gates within the implementation which are vulnerable to a particular fault attack. The alternative is, since at a high level, since this mapping could be done either at the hardware or software, we also have the software equivalent of it, where these locations now would be specific instructions within the binary of the software, which are vulnerable to the fault attacks. So our software tool was called FEDS. It has like 3 layers. One, of course, is the XFC, which is used to identify fault vulnerable operations within a block cipher specification. And then we obtain something known as a FEMA, FEMA. And we also take an input as any source code. So this source code is a realization of this block cipher. For example, it could be an AES implementation. And we essentially map the faults present observed at the output of XFC onto the implementation. And then we essentially do an evaluation where we identify specific memory locations in the cipher which are actually vulnerable to these fault attacks. So the output of FEDS is a set of assembly instructions, or something close to assembly instructions, which are vulnerable to fault attacks. So this would actually permit compilers to be created, which could insert countermeasures only at these vulnerable locations. So here, for example, are 7 different implementations of the Cipher AES, and each cell over here in each of these figures shows a particular memory location. So the shaded cells in each of these images are the vulnerable operations. So what it does mean is that if a fault is inserted in any of these shaded memory locations, it could lead to a successful fault attack. Now, we've done a very similar thing with respect to hardware as well. So just like how software worked on C code, very similarly, we also used XFC to actually work on RTL implementations of ciphers. So you would take the block cipher specification, run it through XFC, have a certain level of transformations, and finally map the vulnerable regions or the vulnerable gates of RTL or Verilog code. And these gates would be actually vulnerable to fault attacks. Okay, so the result would look something like this. If this is an AES a chip, you would essentially be able to identify gates in the chip which are vulnerable, and the shading of the gates would identify specific types of faults, of specific locations where the faults can be actually exploited. Okay, so all of this code is available online. So links are available in the CAD website, or you could directly just download it from this Bitbucket repo. So for the demonstrations today, we'll actually walk you through 3 of these tools: XFC, then Safari, and then FEDS. Okay, so we'd start with XFC. So what I would do is I have the videos, so I'll play the videos and pause them, and then we could actually explain the code or exactly what's happening. So we'll start with XFC. Okay, and so this is what we are doing. So XFC, the Python code takes this thing, this input called the block cipher specification, that is spec_aes.bcs. So we could just go here and look at what this is. So as we did mention previously, this is in a language called the block cipher specification language, which can be used to represent typical ciphers. So it looks something very similar to HTML. You have different functions. You have something additional saying that whether this function is a nonlinear or a linear function, and all the operations that are actually performed by that particular function. So specifically, we're going to trace this function F28. So this function F28 corresponds to the 7th round mix column of AES. So it has 16 component functions, F1 to F16, corresponding to the 16-byte output of the mix column. So we're going to take this as a sample and see how it actually progresses. So so here we specify so here, in addition to the block cipher specification, which is this input over here, we also tell XFC to evaluate for the F32 function, which happens to be the 8th round mix column. And since this 3 is here, we're going to evaluate the output of the 8th round mix column 3rd byte. So essence that if a fault is injected and in this particular byte, we want to know how exploitable it is. So XFC actually gives us that if a fault is injected over here, you get 32 bits of the secret key. Okay, so similarly, we could look at F28 now and the 15th byte output. And what we see is that XFC tells us that the entire 128 bits can be actually obtained. Now, we could try this for every function that is present in AES, or we could automate this entire process with this script called automate.py, where every possible function present in AES is evaluated. This takes a few minutes to run. So we'll just scroll down fast to this. And what we do get finally is something known as is present in this file called output.txt. So the output.txt would give you specific functions which are vulnerable. So these are the exploitable functions. For example, the F2815, which we looked at, is exploitable, and a fault over there could give you 128 bits of the secret key. And similarly, it actually lists all the functions that are actually exploitable. Okay, so so this input, this result can be used by the other tools, Safari as well as FEDS. So we'll quickly see what FEDS actually does, what Safari actually does. So at a high level, what we're doing over here is using the same block cipher specification, using XFC in the automated form, identifying every possible operation that is vulnerable, and then inserting a suitable countermeasure for that particular operation. The result is then used to synthesize either software or hardware implementations. Okay, so so we run the first part where we let me just where we take the input spec_AES. This is the this particular block over here, where the output now is a modified modified block cipher specification where the vulnerabilities are patched in the sense that countermeasures are actually inserted and the exploitable functions are essentially protected. So we'll quickly have a look at that. Okay, let's go quick, to the F28 function, which we are actually looking at all this while. So remember that F28 is the mixed column operation, which looks kind of similar over here, except that that Safari added a countermeasure. It's replicated at the F28 in F29. So it's a redundancy-based countermeasure which was chosen in this particular case. And then the outputs of the two are essentially compared over here, right, using this operation known as FEMP compare, right? So if the output of F28 and F29 are different, probably due to a fault being inserted in one of these functions, it would be flagged and the execution would actually be terminated. Okay, so given this as input, given this as an intermediate output, what we next do is use this to actually create software or to synthesize either software or hardware. Okay, so this is the software synthesis. We now give run the script, which would essentially generate a software which is in this particular form. So we could just go over there and have a look at it. Yeah, so F28 again. Yes, so now we have a C implementation with F28 being replicated in F29 and then the compare instruction, right? Now a similar kind of thing is also possible for hardware. It's also where Verilog can be synthesized with countermeasures already inserted for these for the ciphers to protect against fault attacks. So the output for hardware is now present in this file called here. Yeah, so you have the similar kind of redundancy countermeasures inserted and synthesized in the Verilog code as well. Right. So what we did find out this way was that we could get much more efficient countermeasures inserted, but the implementations are not very optimized, right? So for example, if we go to a different platform, maybe from an ASIC to an FPGA or from a microcontroller to maybe a generic processor, you may actually want to modify implementations and optimize it, maybe insert assembly code. And this was not always feasible with Safari. So what we did do next was have these mapping functions where we had we could take the result of XFC and map it onto an existing implementation. Okay, so we'll be looking at FEDS. Okay, so yeah, just so what FEDS does is that it takes two inputs. One is the source code that you want to actually evaluate. This happens to be imp1.c, which is then unrolled to imp unroll.c. And also it takes the block cipher specification, that is a bcs.c. So what it does do is that it first of all runs XFC on the block cipher specification, identifies operations which are vulnerable, and then does a mapping This mapping would identify where in these input implementations, IMP1 unroll.c, are these vulnerable operations actually implemented. So this way we could go directly into those operations and add a countermeasures to them. There are certain other things that are actually required for FEDS to work. You would need to specify certain type of implementations, whether it is a lookup table based implementation, a bit slice implementation, and so on. This could internally invokes a model checker to identify equivalences between the high level specification that is in the BCS or and the input algorithm, which is the AES implementation over here. So each invocation essentially would have multiple calls to the model checker. The intermediate output would be a set of statements like this. Each statement would tell you a specific line in the implementation which is vulnerable. It would also give you the corresponding operation and how much that vulnerability is. So now that we've actually found out this, we then go into the LLVM, into the compiler, identify how faults can be inserted in those vulnerable statements in the program, and then potentially add a countermeasure to those parts of it. So while it goes on, I could just show you the output. The output would be present in these here, for instance. So it happens for this particular example, we've taken the output of the 8th round of AES. The output is over here. So if in order to corrupt the 8th round output of AES, we would need we would need to corrupt very specific instructions. So this would be actually found out over here. So here, wherever there is, for example, at this particular point, we see that these are the instructions which, when corrupted, could or where a fault is injected, would corrupt the 8th round output and could lead to an exploitable fault. Okay, so you could. So this was a very simple example that we took of AES, which is quite written quite simply meant for an embedded system, but it could also do bit sliced implementation, T-table implementations, and for multiple ciphers as well. So yeah, so that's about it for our for the demonstrations. Our ongoing work is to actually look at something beyond ciphers. We want to look at fault attacks at SOCs and build similar kind of tools. We want to see how aspects such as passwords, page tables, and all could be affected by faults. And this is work in progress. So yeah, in case you'd like to know more, you could contact either Kirti or myself at these email IDs. Okay, thank you very much.
Thanks, Chester. So yeah, so any question? It's a very impressive demonstration. Again, as I said, the tool is available through this link. If you did not really write them down, just go to CAD for assurance, search Chester name, you would see all these tools. And I also would like to ask all of the attendee, if you have your tools, please try to upload the tool to the CAD for Assurance website so that other researchers can also work on top of that.